Hi, my name is Sumith, and I'm going to talk about stability aspects of the nonlinear filter when the dynamics is deterministic. So by this, what I mean is, before going into that, I have to talk about what a filter is, or what does filtering theory deal with. It, it basically deals with a system that we don't know how to observe it directly, but we observe it through an indirect observations. And if both the dynamics and usually the dynamics and the observations are noisy, so we want to construct what is the best estimate of the state from the observation. So to put it in uh, mathematical terms, what we have is we have some kind of dynamics, and you see that there is another equation which models the observations, and d by t is it's saying something about the state, and this we are considering as observation. So, and the underlying noises, at least in the setup that I am talking about, we assume them to be mutually independent. And it sort of makes sense because when you're observing something, you don't expect, at least in classical observations, you don't expect to change the state of the system. So in that sense, B and W are mutually independent, and also the initial state of the system is also mutually independent with respect to B and W. And that again makes sense because the observation noise has nothing to do with how the system started. So yeah, this is the setup I have, and to put it in rigorous terms, when I say the information that I have, it translates into talking about a sigma algebra. And when I say best estimate, it translates into asking this question, which is the conditional probability of the state given the observation. This is how you have to read it as. And it is known that this particular the conditional probability has a nice expression which is this, and this is integration over space of all continuous functions. And this is basically like a base formula in a slightly abstract setup. So yeah, so this is basically like the base formula. And the important thing is this formula depends on the initial condition. So P mu is the law of the Markov process. That was the signal that we have started with. So, and the conditional expectation depends on the underlying initial condition. So in practice, if you're not observing the system directly, you have a very good chance that you are not observing, you don't know anything about the initial condition as well. So because of that, it is desirable to ask this particular question, which is, let's say I use this particular formula, but I replace mu with mu bar, I get something which is pi mu bar t. Now, let's say mu is the correct initial condition and mu bar is the incorrect initial condition, then there is no reason for us to expect that pi mu bar t is the conditional distribution. So the best thing to ask is, how is the difference behaving as you keep making more and more observations? So intuitively, what we might hope is that if the observations are rich enough, then you may not need to know the exact entire information of the initial condition. So that is really what I'll say more about. The problem that I'm interested in is actually when the dynamics is deterministic. So this again is, this has its own practical importance because many of the models that people work with in geosciences are actually deterministic. You have a question? Yeah. It's just a test function, some smooth test function, because it's easy to write it like this because you have a governing equation for this, not for the measure. Yeah, thanks. So the system that I'm working with is the deterministic system, but I still have noise in the observations. So basically my filtering model is just this, and okay, this abuse of notation. this phi t is the continuous flow on some Riemannian manifold, and it has to be complete with this particular initial condition, and initial condition has the distribution mu. So the assumptions that I am going to make are the incorrect initial condition that I am looking at and the correct initial condition that I am looking at, they are equivalent, which means that if mu bar puts measure 0 on some set, mu also puts measure 0 on that set, and vice versa. So just think of it like that, which basically means that from Radon theorem, it basically means there is a density. J is that particular density, and we really want to establish this. Earlier, I just said in some appropriate sense, but what is the precisely in what sense do I mean? It is basically this. I look at this is it basically means that these two measures merge together weakly in expectation. That's how you would read this as. And so to address this question, there should be mu and mu bar actually. So I'm looking at the difference, but as I said, pi mu bar of t need not be the conditional distribution. So, but I can express it in the conditional distribution because of the assumption I made. So this entire thing actually follows from this particular formula, but in place of pi mu bar, you just put j times pi mu, and it's just doing some simple algebra. We get this basically this thing, and this is the quantity of interest for me from now on. What this is really saying is, m is basically I'm pulling out the bound of g, and I am writing it in this form. So what this is really saying is, I am observing, and this quantity is really telling me that what is the best estimate of the initial condition with respect to the observations. Now, let's say if, as I keep making more and more observations, I am able to get much better information about the initial condition, then I would naturally expect that this difference will go to 0. And that is really what I am trying to prove here. Yeah. So, but one has, so I basically want to prove that this is the case in L1 because it is the expectation I am looking at. And this particular quantity converges to a limit that we can show it just from the Martingale convergence theorem, but we really have to show that that limit is actually j of x naught. And that is, that can be shown at least from this and some other calculation later on. So what this is really saying is, this theorem is really saying that if mu is, if mu has a density with respect to the volume that is coming from the metric of the manifold, and if the density is continuous with respect to, if the density is continuous on the support of mu and under some condition that I define later, because I'll stress more on the assumptions. And under those conditions, what I really have is, I take any open ball around x naught with some radius, asymptotically I put all the mass on that open ball, which is really in a sort of vague way saying that I know information about the initial condition better as I keep making more and more observations. And we can extend this result to say that it is actually this. It converges almost surely and in L1, and that proves the stability. But in the remaining time, I really want to focus on the assumptions. So I said under some assumptions. These assumptions are, I have 4 assumptions. They seem like a lot, but really A1 is the sort of the non-trivial assumption. Others are sort of natural, but nevertheless I still need them. So what this is really saying is, as I observe for some time interval, I am really able to distinguish between initial conditions. This is how you have to take it as. So if observations are not really distinguishing my initial condition, then then observations are not rich enough. So I really don't want that case. And this is really encapsulating that particular intuition, that observations has to distinguish between the initial condition. Now, the second condition is really saying that, okay, this is not natural, but this occurs a lot in practice. So what this is really saying is, it's really saying that there is an attracting set for the dynamics, which means if I start in that set, I'll stay in that set. And my dynamics has also, my dynamics started in that set. This basically means that my dynamics started in the set, because mu is the initial condition distribution. And this is basically saying that this is sort of like the Lipschitz condition, if you can see. But what this really says is, it puts a bound on the topological entropy of the dynamical system. It really says that the information associated with the dynamics doesn't, information is not lost at a super exponential rate. At most, it will be lost at an exponential rate. And these things are needed actually to prove the theorem. And wow. And this fourth assumption is really saying that if I want the dynamics to be very chaotic, so that they are not converging to each other, because remember, the result that I'm trying to get is basically via initial condition, which basically means that if I am losing information from the dynamics completely, which this can happen when the system is completely stable, let's say. When the system is completely stable, or everything is converging to, let's say, a fixed point, which means that if you're trying to look back, you don't know where it came from. So that sort of a thing shouldn't happen if we want the result that I'm after. So in that sense, again, that this is sort of like the natural assumption. And yeah, so this is basically saying that the A1 assumption, which is the observations have to be rich enough, all that, and that is really needed if you want to expect anything that we are, that is similar to what we are trying to expect. And this assumption is also very closely related to the well-known assumption in linear case, which is called the observability condition, but apart from the rho t, depending on t, if you see it. In linear case, give me 2 minutes. In linear case, rho t is constant. Here, rho t is increasing with some regularity properties. And the reason is because deterministic conditions naturally have a tendency to lose information via sensitive dependence or chaotic properties or anything, or things of that sort. So what we are really trying to do is, because we want information about the initial condition, you have to make observations at a faster rate than the rate at which the information is lost. That is really the scenario which is at play here. So example for poor observations, which is, let's say that a system is like this, but you're observing only the one part of the system, which means you don't know what this is doing at all. And one trivial example is if it is a full observations, meaning the observation model is like invertible. Again, we need this rate to ensure we are observing at a faster rate. And yeah, this I have already gone through it. So surprisingly, actually, it seems like an innocent assumption in the beginning, in the sense that if the system is chaotic, you may expect this because things are not coming close and they won't stay close. They have to move apart. But the thing is, proving this for like Lorentz 63 or Lorentz 96, I wasn't able to do that, because the only system for which I was able to prove was when the system is anisotropy with very high regularity properties and uniform estimates, and only for that I was able to prove that that particular assumption holds. But for Lorentz 63 and 96, I was able to see that it holds. And asymptotic support of the filter. Asymptotically, its support is on the attractor, which is useful because in practice it will reduce the dimension of the system drastically, because attractor is sometimes manifold. There's a huge difference between the dimension of the attractor and the dimension of the system. And in the future work, we really want to get more details on the support and the rates of the convergence, because we don't have rates of convergence. Okay, thank you. Sorry for taking more time.
Since we have crossed our time limit, so we won't be able to take any questions. If you have any questions, please discuss during the debate. So our next